Chapter 3, problem number 37. An airplane is flying with a velocity of 240 meters per second at an angle of 30 degrees with the horizontal, as this drawing shows. When the altitude of the plane is 2.4 kilometers or 2,400 meters, a flare is released from the plane. The flare hits the target on the ground. What is the angle theta? Okay, this angle theta is the angle that the line of sight makes with the horizon. So a pilot here looking along this line will see the target. The flare is launched from the plane at 240 meters per second relative to the ground at an angle of 30 degrees below the horizon. Okay, we have the altitude, the acceleration due to gravity. So we have a right triangle here. So we could find theta if we knew this distance or this distance. I think I'm going to go after this distance because that I can find if I determine the displacement of the flare. And then once I know the displacement of the flare, I can use the tangent function. So the tangent of this angle is equal to YO over delta x. So I need to find delta x, the displacement. So to do that, I know VO, I know theta. I can find the x part of VO. And if I take the x part of VO and multiply that by time, that will give me the displacement in the x. So the x part is VO times the cosine of theta, 30 degrees. To get time, I have to look at the vertical motion. Okay, and I'll do that right here. Yeah, this will be fine. So we have delta y is equal to VO sine theta. So that would be VO times the sine of theta, but it's directed down, so I have to put a negative sign in front of that. Multiplied by delta t plus 1/2 the acceleration times the time squared. So we have a quadratic equation here again, which I solved for you, and you probably solved several times in previous problems. So I'll just go through this quickly. So I'm going to solve this for time. Okay, now I'm going to substitute in the numbers. And there we go. Now the trickiest part, let me just show you, is this right here. This is the coefficient A, and this is the coefficient C. Coefficient C is negative delta y, the negative of the vertical displacement. But the vertical displacement is the final position minus the original position. In my drawing, okay, I had the final position at 0 meters, and the original position is 2,400 meters. Okay, and that's up, so that's positive. So when you take the negative of the vertical displacement, you have YF, which is 0, minus the original position, which is 2,400 meters. And the negative of that, right here, you end up with positive 2,400 meters as the negative of the displacement. So the displacement itself is negative 2,400 meters, but we have to take the negative of that. So we end up with a positive 2,400 meters there. Okay, so now I'm going to work this out on the calculator. and I get 13 seconds. Now I'm going to take that time and substitute it into this expression to get delta x. So we have the displacement is 240 meters per second. Take that times the cosine of 30 degrees. Multiply that by the time, which is actually 12.979. So I'll just keep 13 seconds. So we get a displacement of 2,698 meters. So the angle that the line of sight makes with the horizon is the arctan of 2,400 divided by 2,698. Arctan of 2,400 divided by 2,698. And I get 42 degrees.